things are presented in terms of numbers and percentages and expressed different ways. And then, for communication, often it's re-expressed in different ways. So yeah, there's a table to do that. One example of the type of things how most people, when they're going to encounter probability, a big form of it is in the tables and counts and subdivisions of the population. Okay, well let's go ahead and get started with some things. Today we'll do a little bit of review on some of the things we've done with counting and some more examples. There's an idea of showing relationships between a couple different ways of counting, and sometimes you can do that with algebra and figure it out, but sometimes you can relate two different ways of counting the same thing through different stories, and just by the logic and the careful explanation, realize that these things have to be the same, and then sometimes there's an algebra way to show it. But sometimes just the stories are a little bit easier, and then a little bit more with counting. We're looking at probability with equally likely outcomes, so that was a motivation for doing a lot of this counting. If we can count all the outcomes that are possible and they're equally likely, and if it's reasonable to believe that, then we can count the number of outcomes that are consistent with some event or some subset that we're interested in and get a probability for that. Right? And so in terms of a little bit of review, right, is that if the outcomes in a set in our sample space, if they are equally likely from the description of the problem to occur, and we have some event A, it's a subset of the entire sample space, then we set the probability that that event would happen when our random phenomenon happens, our random occurrence. It would be the number of outcomes that are consistent with that, and divided by the number that are in S, if they're all equally likely. We had a few rules that helped us with counting. The first essential one was this multiplication rule, that if you're having two separate things and any possible combinations of those two things are possible. So we call this the multiplication rule. The book calls it a fundamental rule, but whatever. We have A and B, and we're keeping track of the two outcomes, and we have n sub A choices for this first one, and we have n sub B choices for the second one, and our choices of the first one don't influence the choices of the second one, but they don't restrict each other in some way. And the total number of pairs of the A and B outcomes is the multiplication. And as you would go with 3 or 4 or 5 different choices, like you might in an experimental design, like varying 3, 4 factors at different levels, the total number of ways those can be put together is the multiplication. Right? And so after this, we took if we have n objects, maybe n subjects or in just objects, and we choose K with replacement. So we allow with replacement. So that means that we allow repeats of the selection, and we keep these in order. So we're going to have a bunch of choices, 1, 2, 3, up to some level. We're going to make K choices that we're going to keep track of all the different choices that we do. We do it with replacement. Applying that multiplication, there is n to the K possible patterns. That would happen. So if you had win-loss for games and you're doing it 10 times, there's 2 to the 10th possible patterns over that. Some correspond to more wins or more losses. But if you kept track of the actual sequence, there would be the 2 to the K possible ones. If we don't allow replacement, So if we have n objects, and we're going to choose k of them again, and we do it without replacement, and that would mean that that each of these is a different choice of those n objects. Each is different. And we're going to keep these things also in order. We're going to have our first, our second, our k's all the way up. Then the number of choices becomes n times n minus 1 times n minus 2, dot, 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 n minus k, right, plus 1 is the number of choices that we get. Right, so it's much less than with replacement and if we have a bunch of selections, because we're using up the population or our objects as we go along and not replacing them, so it's less. And if we did, if we put all in objects in order, then the sequence would go all the way down to 1, n times n minus 1 times n minus 2, all the way down until we have our last object, and that's the final one. And that's what we called n factorial. So we have shorthand for that. So if you have a group of individuals, 6 individuals, you're going to put them in a line, and it would be 6 factorial as the number of ways of putting them in a line. Then we considered things without order, where we just had a set of objects, like a set of cards, a set of people on a committee or a group, a set of animals that we're going to pick out of the population and study them. So then we would have n objects that we can choose from. And we're going to pick k of them without replacement. So they're all different. We don't have any repeats. Right? And then, but we don't care about it. But order is unimportant. Unimportant to what we're going to do. We're just going to look at the set rather than the particular order. The number of ways of choosing this k out of n in this was given by the symbol of n choose k, this combination. And we came about this by thinking, well, we could choose them and put them down in order. Right? N times n minus 1, n minus 2, dot, 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 down to n minus k plus 1 for our k choices. But we don't really care which one's first and which one's second. So of those k things we've already chosen, we could reorder them and still get the same set, right? The same set of cards is there. We usually, in poker, put them in a certain, order anyway to just see them better. And so there'd be k of those that could actually occupy the first position, right? And then k minus 1 for the second position, k minus 2 for the next one, down to 1. And that's how it's a little bit usually easier to calculate by that. We also argue that if you divide by the n minus k factorial here, put it up top and put it down below, it would give an expression like that. So sometimes it's put it in both ways, right? So one way of thinking about how does this be equivalent to this? Right? Well, if you had n objects, you laid them all down. Right? You had the first k, and then you had the n minus k after that. And you have 2 sets. You don't really care what order is in either of those sets. So you could mix all those up on the left side, mix them all up on the right side. You still have the 2 same sets. The same k are picked. Right? And so there's many ways of getting the set on one side and the set on the other, and just dividing by that, adjust for that reorderings. Right? So again, that's kind of a story told kind of 2 different ways. Right? Pick your k and then reorder them, or put them all down and call the first k set group 1 and group 2 and reorder both. Right? They give the same thing algebraically, but there's also kind of a story kind of relating back. Right? We'll kind of use that idea of doing some stories to develop a little bit more, or deal with some cases that look a little bit harder, right? But any questions about that stuff? You use these on the homework and this chapter of the book, but it's kind of putting them together. So let's look at, there's two ways that we get extensions with these. The first one, extension, is often dividing a counting problem into two steps, right? So count part of it one way and then count another dimension of it and multiply those together. Right? So a first extension of these is essentially divide a counting problem into steps and then count in each step, right, and then multiply. Sometimes thinking about things in pieces as you assemble the objects that you're counting helps out. Right? So a classic example of this is in poker. There's 52 cards in a deck of cards. Each card has a suit and a value. Right. There are 4 suits and 13 possible values, and so that gives us our 52 unique cards. And a hand in poker is you pick 5 cards without replacement. And order doesn't matter, right? You just have your set of 5, right? You can rearrange them in your hand and it's still the same quality, the same score, right? Unordered. Right? So how many possible hands are there? Of these different counting things, which one would this one be? So it's picking without replacement, right? So the numerator has to go down, right? 52, 51, 50, 49 choices, and 48 choices for the next one, right? We don't care about order, right? So we could reorder those 5, 5 times 4 times 3 times 2 times 1. And so that's our 52 choose 5. Is that combination 1? Correct. Right, to calculate that out, that's 2,598,960. Right? And assuming you're being fair and not trying to hide cards or something like that, all those hands, those 2.5 million, should all be equally likely. Right? Any questions about? So, what's the probability that all 5 cards have different values? So you dealt 5 cards from the deck. What's the chance you don't have any pairs of numbers? You have all 5 different values. Couple ways to go about it, right? One way, right? Well, any suggestions? How would you want to kind of start this problem? We'll go through a couple, but just think about it for a minute. 52 cards, 13 different values, we need 5 different values. So, how many ways are there choosing? So this is going to be an example of the 2-step divide and conquer type of thing, right? We need 5 different values, right, from the 13. Out of the, how many ways are there to choose 5 different values from the 13? Without replacement, unordered, just a set of 5.
13 choose 5.
Yeah, 13 choose 5. Before we were picking out of all 52 cards. Now we're just saying, let's take the first part, let's pick the values. Right? So we get 5 different values. We get a 2, 3, 7. We get a 10, and we get a king as 5 values. Right? To make it a card, each of these values has to have a suit. Right? It either has to have the club, diamond, hearts, or spades. Right? How many choices do we have for the number 2 to make it a complete card?
4.
4, right? How many choices do we have for the 3 to make it a complete card? 4 as well, right? And so this is, there's 4 to the 5th choices for suits. So here we choose the values, here we choose the suits. And so that number ends up being 1,317,888. And so the probability of this 1317888 over this other number, 2598960, is about 50, a little over 50%. So about half the time when you're just dealt 5 cards from a shuffled deck, you're not going to get any pairs, any matching values. So this is an example of this 2-step thing, where we can pick the values and then pick the suits, and that makes it, it's one way to count it. There's another way to count it, right? That's equivalent. Right? What if you pick 1 card? Right, we get 52 choices for our first card. How many choices can we make for our second card that do not match that same value?
15.
Well,
-4.
Yeah, to -4, right? We can't pick that one, we can't pick any of the other ones. Say we pick the 2 first, right? Then we can't pick any others. So we get 48. Once we have the 2 and say 7, right, that eliminates 8 possible cards for the third one, right? So we could do 44, and then 40, and then 36. My math is right. But by thinking that way, we'd be putting things in order. We pick the 2, and then the 7, and then the king, and then the 10, and then the 3 as one particular order of those. Right? And these things would have suits. So here's the heart. This maybe the king is another heart. This is the diamond, and clubs kind of looks like that. Maybe these are clubs, right? So they're full cards, right? But they're in a particular order, right? And so we don't care about order because we just need that set, so you have to divide by 5 times 4 times 3 times 2 times 1 would be a different way of counting the same thing. And these things are equivalent, because what's 13 choose 5? Well, it's 13 times 12 times 11 times 10 times 9, and in the denominator it'll be 5, 4, 3, 2, 1. But 13 times 4 is 52, and 12 times 4 is 48, and so on. So you can do it kind of directly like this, picking cards, and then thinking about how picking one influences the next ones. Or this kind of this 2-step process can be done. But any questions? How about how many ways can we pick 1 pair? So a hand of cards in poker that has 1 pair has 2 cards with 1 value, and then 3 other values on those cards. So you get like a 2 and a 2, and then 7 king 3. Right? And so there's the pair of cards that are there. Right? How many ways can that happen? You dealt 5 cards. What's the chance that you're looking at your 5 cards and you have 1 pair of some sort? So breaking it into pieces, right, can help. Right?
Are
Yes.
you saying at least 1 pair or exactly?
Exactly 1 pair in this case. So we need, how many values do we need in all to make this work out? 4, right? So we could choose 4 values, right? But one of those values is special, right? One of those values is for the pair, and the other are the singles. Right? So once you pick those 4 values, you need to choose one, choose the pair value. Right. So now we've chosen, say, 2, 7, king, 3, and now we've chosen the 2s to be the pair. Now to complete the cards, we need to add suits onto them. Right. So it's kind of another step, kind of this multiplication rule used to do that. How many choices, and we're going to take the 2 different things. We're going to pick suits. There's a little bit of difference. Choosing suits for the pair versus choosing suits for the singletons. Right? There's 4 suits. How many ways can we choose suits for these 2s?
4 choose 2.
There's 4 choose 2. Right? There's the 4 different types. So these are the suits for the pair. And then the singletons, each one of those has 4 choices, which is 4 choose 1. We do that 3 times. And so if we put that together, that counts this problem. So by breaking it into pieces, it works out that one pair happens 1,098,240 times. And so the probability, if you take the ratio versus the 2.5 million denominator, is about 0.423. Do one more of these to kind of get this practice. Right? 2 pairs, right, has a pair of values and then a different pair of values on 2 other cards, and then a third single value. So we can have 2 2s, 2 kings, and then a 7. And so this would be exactly 2 pairs and not 2 and 3 or something like that. Right? How many ways can we go about counting the number of 2 pairs? Yes.
Do you start with 13 choose 3?
You can start with 13 choose 3, right? So we need 3 distinct values. You got to choose the 2, the king, and the 7, something like that. So there's a little difference between how those values show up, right? Some couple in pairs and 1, right? So we have 3 values now. We would choose 2 of those to be the pairs. And then this would say which ones are the pairs. And so this would be saying the 2 and the king are our pairs. Right? And the 7 is going to be a single thing. Right? So we know our values, we know which ones are doubles, which ones are singles. Now we have to choose the suits. Right? Essentially there's 3. So for the 2s, we have to choose the suits. Right? And there's 4 suits, they need 2, they need clubs and hearts or something like that, right? So there's 4 choose 2. That can be for the 2s, the kings also has 4 choose 2. And then the 7, we just have to choose one of those. Right? This thing ends up being 123,500, I think 72. I might be off because I'm not sure if the right number says. The probability, if you calculate that, is about 4.8%. So if you add up all different, 1 pair and 2 pairs, actually you get about 97%, almost 98% of the hands that you're going to get dealt just by getting 5 random cards are going to be like that, right? The other ones that are automatically dealt with 3 of a kind or some other interesting pattern are more unusual, right, than that. But any questions? So, right. You don't have to become an expert on cards, but this is kind of illustrating very the sequential thing. So that's one extension. One way you can deal with harder problems if you're looking at a population that has different characteristics. You know, you have men and women, you have age groups, you have education levels, and you're trying to pick people. Well, one way of thinking about that is picking from one step set and then conditional on you pick that first one, you can pick the next one, and so on. Kind of doing a branching process. In a way, it's kind of kind of a sequential of steps. So I call that one extension on using the rules that we've done so far. A second extension, right, is partition into 2 or more groups. The extension really is into getting in multiple groups. Right? So let's say we have 12 people. And we want to divide them into 3 groups of 4. We're going to make 3 different study groups, 3 different project groups of 4 people each. How many ways can that randomly be done? So we're dividing everybody up. I guess you could say it's without replacement, because nobody goes in 2 groups. It's unordered. We're just saying here's a group. There's 1, 2, 3 people in a group. We don't care which one's first, second, or third. They're just together. Right? How many ways can that be done? Of our people, right, you could give them labels A, B, C, D, up to L, right, or 12 letters. Right? And then we're going to have, you can, sometimes it's easier to go back to thinking about things in order and then undo the overcounting like we did with combinations. So 1, 2, 3, smaller. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So here's 12 spaces. So one way of thinking about forming groups is to take these letters, randomly shuffle them, and put them down in order. Right. And then call this group 1. And then the next 4 becomes group 2. And the next ones become group 3. Right. But we read, so if we kept people in order like that, how many possible ways are there of putting the letters A through L down, keeping the people in that order?
Factorial.
There's 12 choices per second, times 11, times 10. Right? We're not repeating anybody, so the numbers go down. So there's 12 factorial in order. So maybe we do in fact choose A first, and C, and L, and J, and then B, D, H, and I, and what I leave? A, B, C, D, E, F, and then maybe G is the last person, H, I, J, K, right? So that maybe that's how it ends up being, right? So A, C, L, J is our first group, B, D, H, I is our second group, and E, F, K, G are the people in our third group, right? But if we don't care about order, we get the same groupings whether we shuffled the orders in here or not. Right? So how many ways are there to reshuffle those 4 people? 4 factorial, right? So there's 4 factorial shuffling of the first group, there's 4 factorial shuffling of the second group, and there's 4 factorial shuffling of the third group. So this is the number of ways to partition 12 into 3 equal-sized groups. Does that seem to? Yes?
So what if you just like choose 4 people as a group at first and then try to decide the second group? So can you do like you choose 4 in 12 and then choose 4 in 8, get the same answer as what this will do?
Right. Let's think. So you could say choose choose 4 for the first group as a 12, right? So choosing 4 for the first group should be our 12 choose 4. Okay? And then you choose 4, and it'll break up this one into 2 parts, and you get 4 and 4. So there's 8 left over, so 8 choose 4.
It's same.
Right. So let's see if it's the same, right? So 12 factorial over 4 factorial over 8 factorial is this first one, right? And then 8 factorial, 4 factorial, 4 factorial is that next one, right? And so the 8's, right, cancel it. And that's the same partition. Right? But it's fine, it's good to think about it that way too, right? So that sometimes you can do it in steps, and that simplifies the process. So, okay. You check it by algebra, or you can check the, kind of a logical story. You almost are convinced that it should be the same thing. You pick the first 4, then you pick the next 4, and you're done. So we would want it to be the same number, and kind of this is the algebra or the numerical example to show it. Just to do a little modification of this, we have 12 people, and we're going to pick 3 groups. But the first one has 6, the next one has 4, and the next one has 2. There's different tasks. Right? How many ways can we assign groups? It's going to be a similar type of process. You can think of it as putting 12 people in line, calling the first 6 the first group, the next 4 the next group, and the next 2 is this group, which is 2. Right? So instead of dividing by 4 factorial, 4 factorial, we could reorder those 6 to the first group, and then 4, and then 2 should give us the answer. Or if we think about picking 6 for our first group, right? 12 choose 6 would be our first choice. Pick 6 people to be in the big group to do the whatever task that is. How many people are left over for this next group? There's 6 left over. Right? And to make the second group, we need 4. Then there's 2 people left over, and we need 2. So 2 choose 2. In general, n choose n, or n choose 0. These things are all defined, are all 1. The way of picking n people out of n, there's only one way of picking that. There's a little special case with these 0 factorial. If the factorials go n times n minus 1 times n minus 2, that doesn't quite work for 0. But 0 factorial is just defined to be 1. There's only one way of doing nothing. But in any case, these things should be the same, right? If you expanded these out like we usually do, you'd have some cancellation. So that's kind of an second extension. We can deal with multiple groups there. So that's kind of what we've done with counting. Sometimes we can see relationships by telling stories, these some kind of story proof or justification, where it's clear that we are doing counting to get the same answer, like these type of things that we've just done. You can look at it either way, and they should come out to be the same, right? So one relationship like this is that n choose k is the same as n choose n minus k. Why is this true? why do you get this relationship? All right, so if n is 8 and k is, say, 3, 8 choose 3 is 8 times 7 times 6 over 3 times 2 times 1 is one way of calculating that, and so that was 56. And then 8 choose 5 is 8 times 7 times 6 times 5 times 4. We go down 5, and then 5 times 4 times 3 times 2 times 1 is the numerical value. These 5 and 4s, if you cancel those portions up there, you see that they're the same, and it's still 56. Right? So in that one numerical instance, it's clear that it's the same. What we're saying is that it's always the same for any integers n and k, where k is less than or equal to n. Why is this true in general? There's a couple ways of talking about why you believe this is true. One is an algebra way, and it's fine to do that, particularly in this case it works out easily enough, right? What's the algebra way? Or algebra, or dealing with math symbols, right? Manipulating the math symbols so that the left-hand side is the same as the right-hand side. Right? What's in choose k in symbols? Going back to our, yes?
Factorials.
So if you write it with the factorials, n factorial, k factorial, n minus k factorial. Right? But in the denominator, right, it's equivalent if you, our multiplication is commutative, so we can switch those, right? And that's the same. But written like this, that looks like what would be n choose n minus k. This thing, you have n, and you have n minus k factorial, and then you take n minus n minus k, and that's just k. So this thing, factorial, is really just k factorial. So the two things algebraically are the same. But what's the story that goes along to, what type of story or scenario can you describe that would make this, oh yeah, that's true, right? This is often called choosing, right? You have 10 people or 8 people, you need to choose 3. You have 8 items, you're going to inspect 3 of them, right? Give 3 to your friend, and so you need to pick 3 out of those 8. Right? Well, picking 3, the alternative of, the opposite of picking them is not picking them. Right? So if you pick 3, you leave out 5. But if you kind of viewed it the other way and said, I'm going to leave out 5, and then I'm going to have my other 3, right? There's a dichotomy there. And so either picking 3, marking these 3 to be used, or marking these 5 to keep, right, is equivalent process. Right? So the counting of that process, whether you view it as picking 3 or to ship away, or picking 5 to keep at home, right, should give you the same number. So writing that in a few sentences kind of says, well, if I pick k, that's the number. However, if I pick n minus k to leave out, that's the number. Since those two things should be the same, right, the numbers match up. So sometimes you can tell some stories like that put things kind of equal together, right? So here's a little second story. So let's say here's an equation. N time n minus 1, k minus 1, and k n choose k. Is this true? Are these combinatoric things the same? There's one way to do this with algebra, But you also can tell a story in a certain way to make these things look similar. Let's do the story first. Right? So let's say we have eight individuals. Now we want to pick K or a team. And the team needs a captain. One of those K, not another person, one of those K is the captain. How many ways can we randomly pick K people from the team and make one of them the captain? Does one of these formulas kind of count this or make sense as counting to you? As I've phrased it, I think it's a little more consistent with the right-hand side. How many ways are there picking K people from for a particular team?
Choose K.
And choose K, right? And thinking about one of those extensions where we do kind of things in two steps, right? Then we pick a captain. How many ways are there to pick a captain from that team of K? There's K choices, right? So this would seem to be, right, K choices here, multiply those to get those together. Is there any other way of getting our team and the captain besides doing it that way? Can we look at it in a different order and still come to the same grouping of people? Yes?
Would the first equation be kind of like pulling the captain out first and then choosing the other remaining Ks from what you have left?
Yeah, exactly, right? Because in people, you need to choose a captain. Right? Let's choose the captain first. Right? And now once that captain's on the team, there's n-1 people left over, and you need k-1 of them. Right? So that's picking the captain first, and then the rest of the team. This one is picking the team, and then identifying who's the captain. Right? And so those two stories should end up with the same result, the same group of people, right? The same number of ways of doing it. So this other one, as we said, is pick a captain. And there's n ways to do that. Captain. And then select the rest of the team. N-1, k-1. Because we've already filled one slot on the team and we've taken one person out of there. And if you multiply those together, you get the left-hand side. So if you believe that those two stories tell you the same thing, and I think that they do, then you get the same number. Any questions? Does that make? You could always, kind of check some of these things with a numerical thing, just to kind of get a sense of, if n is 8 and k is 3. The left-hand side is 8 times 7 choose 2. 7 choose 2 is 7 times 6 over 2 times 1. So that's 56 times 3 is 168. On the right-hand side, k, we're choosing 3 people, right? And then wait, no, we're choosing, because 8 choose 3, and then 3 following, so selecting the numbers. So 3 times 8 times 7 times 6 over 3 times 2 times 1. And there's a cancellation here of those 3's. And so again, you're getting 168. Right? It works out in a particular numerical example. Sometimes working through a particular numerical example kind of gives makes it a little more concrete. But if you wanted to show it with algebra, right, with numerical symbols, right? Right, one strategy is to take the left side, okay, and take the right side, right, and then start expanding what those symbols mean. Right? and see if you get to a point where the two come together and are exactly the same in terms of the symbols. I'll do the bottom one, because this is n factorial over k factorial, or n minus k factorial. Can that lower one be simplified? What happens when you have the k over k factorial? K over k factorial means k over k times k minus 1 times k minus 2 all the way down to 1. So that first k can cancel there. So it's 1 over k minus 1, k minus 2, all the way down to 1. And that's 1 over k minus 1 factorial. That's simple. So this thing can be written as n factorial over k minus 1 factorial and n minus k factorial. A couple steps there, right, to kind of simplify that. Let's do something on the top and see how it goes. Okay. There's n, but what's n minus 1 over k minus 1? N minus 1 choose k minus 1. Kind of follow the same factorial. Right? N minus 1 factorial, k minus 1 factorial. And then we need n minus 1 minus k minus 1. Right? So the difference between n minus 1 and k minus 1 is just n minus k. N minus 1 minus k minus 1 is just n minus k. The difference there. Well, we're pretty close already, right? In the numerator, what is n times n minus 1 factorial? Or that's going to be n factorial, right? Because n and then times n minus 1 times n minus 2 all the way down. Well, that's what this gives us. So this is n factorial, k minus 1 factorial, n minus k factorial. And these two things are the same. So those two expressions are the same. And that would be using the algebra, using the math symbols to show the equivalency. Right? But we also kind of got that insight through the story problems, right? Kind of expressing it that way. But any questions? So we won't do a lot of manipulation of those. As we get into things like the binomial distribution or multinomial distribution, those involve a little bit of the combinatorics. So having done this, we'll make that easier once we see it for a few things there. The area of combinatorics and graph theory and some things of that, we do a lot of counting of different combinations and subsets and things like that. And then knowing kind of the relationship between some rules helps in some things when you're adding up and doing some other manipulation. So it's you don't have to memorize a ton of these things. I'm more interested in kind of the process. That in some cases we can tell stories, we can do a little bit of expansion, we can put in some numbers. Right? So we do a little bit of this to get a flavor of what it is and how the math goes. Let's look at one more, a third story. There's an equation that's van der Waals. So some things in probability have names on them. This is one. It's not mentioned by name in our particular textbook, right? But in this case, we have n plus m people. Or they're really just n of one group and m another one. Let's say that there are n females and m males in there. And we're going to pick k. K for a group together. Now let's say, for simplicity, that k is less than or equal to m, so k is less than or equal to m. So we could pick all females or all males. How many ways can we pick this? Now, for the time being, ignoring that there are males and females, just how many ways can we pick K people from the total set? M plus N people, or N plus M. And we need to choose K, so there should be N plus M choose K ways to pick those people. That's the first part. N plus M choose K. What happens if we keep track of the number of females and number of males that we pick? Let's take a special case. Suppose we pick J females. J, there are females. I picked males. That's how I expressed it here. So I'm going to keep it the same in my notes so I don't get things backwards. We get J males. How many females have to be in the set? K minus J, right? So K altogether. How many ways are there picking, particularly J males and K minus J females, out of the set of people we have?
What's the male?
Males was M and females was N. I just matched up M and N here to try that.
So it's just choose J and choose K minus J.
Right, so out of the males, right, M choose J. And out of the females, N choose K minus J. That'd be the number of way of picking K individuals when they split that way out of the males and females. But that's not the only way it could split, right? J could be a bunch of different numbers. So we could split it different ways and still get answers. What's the range of possible J's? Yeah. So J could go, right, 0, 1, 2, right up to K. And so if we added up the number of ways of picking J females and K minus J, and we calculated for all those different things and added them together, shouldn't that be what we had before? Right? So this equation says that N plus M choose K is rewritten as a summation on J going from 0 up to K as its ranges of M choose J times N choose K minus J. So this is the equation, this Vandermonde equation, that M plus M choose K can be split into a sum where we are considered the two groups, and those two should be equal. It's a little more, right? If you're just given this and said show it with algebra, that that's a little bit more of a big deal to think about, right? But for this story, I think it's reasonable to say it's the same, right? We can look at it as an example, right? So let's say we have 3 females and 3 males. Small numbers are easy to deal with these. Right? Now we're going to pick 3. We have 6 people. And pick 3. How many ways can we do that selection to get our set of 3? Right? We're not caring about order. We're just need this set of people. Well, 6 choose 3. Okay, 6 times 4 times 6 times 5 times 4, and then 3 times 2 times 1 is 20. Okay. That's the easy side, right? On the right side, what we call J could be 0, 1, 2, or 3. So this was counting the number of males, I said. You could do either females or males. In this case, it's balanced at 3 and 3, so it, so if the groups have 3 and 3, you need 3 overall. One way of constructing that is to get 0 from one group and 3 from the other. But you can also get 3 total if you take 1 from one group and 2 from the other. Or 2 from the first group and 1 from the other one. So if you want, say, this is males and females, and this is the 0 and 3, 1 and 2, 2 and 1 is different than those. Or you could get all 3 males and 0 females. And choosing 0 of something, right, is one. There's only one way to choose 0 of something. You have to choose 3 of the other. So it doesn't work out quite that easily with the factorial formulas. But just if you think about the story, how many ways can you pick 3 out of 3? Well, you can pick them all. So there's just one way to do that. So sometimes the story. So this is 1 times 1 plus 3 times. Now 3 choose 2 is also the same as 3 choose 1, right? Because of the subtraction. So that's 3. This one is 3 times 3. And this one is 1 times 1. So it's 1 plus 9 plus 9 plus 1 is 20. Right? And in this numerical example, they're the same. But we got the bigger formula by, it's easier to think about it with a story. And we're not going to have ones quite as involved as that on an exam or anything like that. We'll do some more practice. But it's kind of, as you get used to it, and it takes some time to see different problems and work through different ones and see different reasoning. And sometimes the story is not all that straightforward to come up with out of your head. And so, but it's something that with practice, you can count for things that are pretty complicated and be fairly accurate. But any questions about? There'll be a few more combinatory counting type problems of some types on the next homework to illustrate some of these. You just kind of build on what we're doing. Right? And so what we want to do is look at one new thing. This is in book section 2.5. One other form of counting. These equations sometimes are called the Bose-Einstein equations for counting particles of different types. And in this case, there's n objects. Right? And we're going to pick k times width replacement. And k objects, or maybe sometimes these are called types. In the application to particles could be there's different types of particles. And you're going to pick different particles. You pick k times with replacement. Replacement, in the example of particles, there's a huge number of particles. So picking one doesn't really diminish the number in any meaningful way. If you go from 10 billion down to one less than that, it's not changing the mix so much, right? So we think about it as with replacement, but order doesn't matter. So we're really counting how many times. Right? So we are really counting how many times is each type or object picked. You're picking 1,000 molecules. How many hydrogen would you get? How many helium would you get? How many oxygen would you get? And so on. Right? This is a little bit different from the other ones. We've done unordered without replacement, and we've done ordered with replacement. We haven't quite done this one. What makes this one is a little bit the number of duplicates that arise. It's hard to count those because if if you try to put them in order, the number of ways that, you can get 2 of a kind or 3 of a kind, there's a lot of different ways to count that. So it's not quite as easy. We can tell a story that maps into this problem that gives us a formula. So how do we count the number of times each object gets picked in this? Right? Well, one way of phrasing this is to set up in bins or little boxes. Right? We're going to put them here beside each other. Right. So here's number 1, number 2, number 3, dot, 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 right up to n. And we're going to drop the outside lines from this picture. We're going to keep the inside ones, but drop the ones that are outside. Up to n. So how many lines are remaining? How many lines remain in this picture? Close. Yeah, n minus 1, right? So the way it was drawn, there's n bins, but there's a left and a right endpoint. So 1, 2, 3, and then this would match up to n, but there's that one extra. So this had n plus 1 lines. And if I drop the 2 endpoints, we're down to n minus 1. Right? So one way to think about the sampling, picking k times, is imagine you had k balls. And you're going to drop the balls into these bins. And each time you drop a ball in there, right, you represent it. So if it landed here, that would be a 3. Here's another 3. And let's see, 4, 5. Oh, right. So you drop one here, and then you get a couple over here. Right? This sample, as depicted up in here, would be 3, 3, 5, n and n, whatever our largest number is there. Right? So that's 5 drops, 5 balls in there. K equals 5 selections. And I don't care what order it is in. I could have done the n's first, and then the 5s and the 3s, or the 5 first, and mixed them out. I still get the same set. Right? So this process of picking with replacement, allowing duplicates, right, but not caring about order, gets represented by this picture, by this story. Does that seem pretty neat? Whoever thought about it, puzzled about this a few times about how they think about this thing. But anyway, that represents this process of what we're asking. Sometimes we can do it very straightforward with some numbers, particularly if it's without replacement, right? Because there's kind of a sequence, or you could draw the steps. So sometimes we'll do it different ways. This particular one is a little trickier and special, so this story work. So now the question of how many ways are there to do this corresponds how many ways are there of, let's think about this. Right? So we have n minus 1 lines. How many balls and lines together?
N plus 4?
N plus 4 in this case, yes. There's n minus 1 here, plus the 5 is n plus 4. In general, it'd be n minus 1 plus the k balls that would go in there. When it's 5, like my picture, then it's n plus 4, right? So the process of sampling, right, is equivalent to taking n minus 1 plus k, or n plus k minus 1 objects, calling k of them balls, and calling n minus 1 lines. Number of ways of sampling in this case is equivalent to the number of ways of choosing objects, k balls, and n minus 1 lines. So you have these things in a sequence, and first you had your k balls, right, on number 1, and you'd have k copies of number 1 and nothing of everything else. Right? If all the balls are on the very end, you'd have k copies of n and nothing else. And if they were just kind of, however they're scattered in there, in that order is going to determine that. Right? So one example, right, of this is like, just threw down these lines and balls in this order. So it would look something like 1, 1, 0, 0, 1, 1, 0, and then there's 3 lines there, and then 2 like this. Right? This picture would mean here's 1, 2, here's 3, 3. Those are included in the sample, or 5's included in there, right? And then 6, 7, and these, say these are 8s. These are my big numbers n, and I have 2 copies of those. So this kind of sequence throwing down there represents the sample, right? Every time we choose a different sequence, we get a different, so we need to choose that, right? So this is reduced to a combinatorics thing, right? N plus k minus 1, choose k. Or equivalently, n plus k minus 1, choose n minus 1, which is easier to calculate, and that would be the number of ways to calculate that. So just a little example. Right. So we have a little game at home called the Sneaky Snacky Squirrel, where there's a tree and there's acorns and there's a spinner, 0, 1, 2, 3, and spill. Right? And the idea is you want to fill up your bucket with acorns. You spin the spinner. If it lands on 1, you get to pick 1 off the tree. If it spills, then you have to put it back over and start again. Right? So, now let's say you spin 8 times. It's with replacement because you can repeat the numbers. Right? So repeats are possible. And let's say you spin, right, so you spin 8 times. How many right, so what it would be, sets of numbers are possible. So this is trying to express not keeping track of order, so unordered, right? I'm not keeping track of, did I get a spill, then a 0, then a 1, then a 2 in particular order, but just how many different 8 times did I get 2 spills, a 0, a 2, or 3, something like that. So if this fits that Bose-Einstein formula, right, we have what? N equals 5 categories, or observations, 0, 1, 2, 3, and spill. Right. I'm doing it 8 times. So how many possibilities? How many ways is it possible? Well, this thing, the formula was n plus k minus 1, and then k. So in this case, you put in the numbers, a plus 5 minus 1 over, choose 8. So that's 12, choose 8. But that's not as easy to compute. 12 choose 8. So it was K, right? Yes, K, right? I'd rather compute 12 choose 4 by hand. So 12 times 11 times 10 times 9 over 1 times 2 times 3 times 4. So that's 12 and 10, 5, so it's 45, 495 ways that you can have something like that. So one sample pattern, 0, 1, 2, 3, and still, or your piled 8 for. You've done it 8 times, so one type of sequence, that might have happened once, this might have happened 2 times, maybe you're unlikely and you have 3 spills, so that's 6, and maybe you get 2 of these and that doesn't happen, right? So these are the objects you have, and these are the repetitions that you would have, and so you could get different variations of this that add up to 495 ways. I don't think I've seen all of them, but seen a few, right? So anyway, that's kind of one application of counting of that. But any? Yes?
How did you get from 12 choose 8 to 12 choose 4?
From 12 choose 8 to 12 choose 4. This is always going to be have a neat, a useful relationship. You can choose 8 things and leave 4 out, or choose 4 and do those others, right? This is the in the general case, n choose k, or the book uses r. I don't know. I just as a number of responses ends up being true, right? So when I'm doing it by hand, that's the fast, the smaller number is easier to do. So one more application of this is, let's say that you have Democrats and Republicans. So we have essentially two categories here, and we're going to pick people. We're going to pick at random. And we're going to count the number of Democrats and the number of Republicans. How many different sets of counts, number of Democrats, number of Republicans, can we have, right? So this is with replacement. We're going to repeat the Democrats, Republicans. We're not caring about order because we're just counting the numbers. We're not caring about who was first and who was second in our picks, right? So it fits that Bose-Einstein equation. How many different possible outcomes for Democrats and Republicans there are, right? So if n is 2 and k is 12 picks, right, the formula says n plus k minus 1 choose k. So that would be 13, k is 12. 13 choose 12. The equivalent to 13 choose 1. Ways, it's just 13. It's only 13. Why is it 13? I calculated, I said, well, why is it only 13? Well, if you're only counting the number of Democrats and Republicans and picking 12 times, what are your possible outcomes? Pick 12 people. You're going to tell me now how many are Republicans and how many are Democrats, right? Where they have to add up to 12. What answers could you possibly give me? If everybody's Republican, right, it's 12 and 0, or 0 and 12, right? But if there's 11 Republicans, there's 1 Democrat, so 11 and 1, right? Those are the only answers that are going to come out of that process. So the possibilities for the number of Democrats and number of Republicans, like 0, 12, 1, 11, 2 and 10, etc. To the point that we have 10 Democrats, 2 Republicans, 11 and 1, or 12 and 0. And how many of these different possibilities are there?
13.
There's 13 ways that this can happen. And so that Bose-Einstein is counting those ways. So that would seem to work. Any questions on those? We'll do one more story, one more example. Here we have Pascal's triangle. Right, so Pascal's studied numbers and counting and probability. Pascal's triangle goes like this. We put 1 up here. You put 1s on the edges of the triangle going down. And the thing that you put in the middle is this is the sum of the numbers that are diagonally above it. So a 2. So the next row, you get a 1, and the sum of these two things is 3. And the sum of these is 3, and there's a 1. And then 1, these add up to 4, these add up to 6, these add up to 4, and 1, and so on. 1, 5, 10, 5, 1. And surprisingly, there's a lot of different relationships in this, right? That can be thought about in terms of combinatoric. Right? So we're going to put levels on this. This is going to be our level 0. We're going to call it level 0. Call this level 1. Call this level 2. Call this one level 3. Level 4, and level 5. You know, you keep going, something like that. What do these levels add up to? What's the sums that are there across the levels? Obviously 1 after the first one. And then 2 numbers there. What's the next one? 4, and then 8, 16, right? So you see a pattern going there, 4, 8, 16, 32 powers. Right? So at level n, level n, the sum is going to be 2 to the n, following that kind of inductive pattern there. So we can go down these sums and say at level n, it'd be 2 to the n. 2 to the 0, 2 to the first, 2 squared, 2 cubed, and so on. But what's this thing that we're adding up in here? Right? There's something underlying this. There's some other story that if we add up these numbers going across here, we get that 2. What's the pattern that's going on? Well, let's think about if you have x plus y and raise that to a power. Well, x plus y, let's say to the first power. For the first power, that doesn't change anything. It's just x plus y. What if you do x plus y squared?
X squared plus 2xy plus y squared.
2xy. You know that, but what are the multipliers on that? Here's 1, here's a 1. Right? And there's 1 on this, and 1 on that. How about if you cube it? again, if you put a 1 here and a 1 here, right? So you get 1, 1, 1, 2, 1, 1, 3, 3, 1. You do another one. You get x to the 4th, 4x cubed y, 6 x squared y squared, 4x y cubed, and then y to the 4th. You think about these as ones, right? 1, 4, 6, 4, 4, 1. So there's a matching of this pattern that's going on. Kind of neat, I think, that it's coming out of there. What are these coefficients? Where do those? What's another way of looking at those coefficients? What happens as we take x plus y up to some power? Let's do the end. There's an x to the k and a y to the n minus k term, right? That in these terms, what do the exponents always add to? X to the 4th, this is 3 and 1, and 1. This is 2 and 2, this is 1 and 3, that's 4. So every time you add another x plus y, right, it contributes to either an x or a y to the products. Right? So if you did another one, right, there'd be an x to the 5th, but there'd be either x plus y times this particular term, it'd be x to the 5th, or x to the 4th times y. So again, there's going to be 5 terms if there's 5 things product multiplied together. So what's the multiplier out front there? In terms of combinatorics, in terms of things that we counted. Let's see. So, let's see, we can do x times x plus y times x plus, x times y plus y times y. Okay? So when there's 2 things multiplied together, every thing that you expand has 2 in there. A certain number of x's and a certain number of y's. I won't write it with 3, but if you have n x plus y's together, right, you get x to a power and y to a power. And each one of these, x plus y, da da da, up to x plus y, right, n times, each one contributes either an x or a y. So how many ways can we get kx's and n minus k y's? Sorry, in
10 ways.
A little bit more than that, actually. So
UN?
there's something related to 2n will be is some other connection, right? So that's connected there, right? So, but there's an n choose k multiplier up front. All right, we have n terms. We either have to pick an x or a y. So how many different ways can you get k of the kx's n minus k? Right? So you have to pick out of these n, you have to pick k. To contribute an x, and the other n minus k contribute a y. Okay. And so that's going to be the multiplier there. Right? But we're summing over that. So here for x cubed, there's one way to put up all x's. 3 choose 3 is 1. 3 choose 1 is 3. 3 choose 2 is 3. 3 choose 0 is 1. So what comes out of this is this identity of x plus y to the n. Well, there's an x to the k term, and then there's a y to the n minus k term. And this configuration is going to happen in choose K, but we're add over all these different bits, different values of K going from 0 to n. So x plus y to the n actually is equivalent to this. This is sometimes called a binomial expansion. These are our combinatorics. They're also called binomial coefficients. In there. It's a little bit more involved completely as a big example, but it uses some of the elements that we've done with counting. Any questions? You want to go back and look at any other part of this to try and appreciate it? So we were looking at this thing adding up to there. We'll do a little bit more with that. And this one either contributes 1x or contributes 1y. This one with 2, it either contributes 2 x's, and there's one way to choose it. You choose x, and you have to choose x. There's 2 ways to contribute an x and a y. You choose an x and a y from the first one, and a y from the second one, or a y from the first one and an x from the second one. Right, they're the product here. And you get 2 y's, you have to choose the y on both ones. So there's only one way to do that. Once you get to this one, how can you get x squared and y? Well, there's 3 parts over here, 3 equations. Right? 2 of them have to contribute an x, and 1 of them has to contribute a y. So there's 3 choose 2 or 3 choose 1, whichever way you want to look at it. But 3 ways to come up with this, and say the same way 3 ways to do that. And so it keeps going in that expansion. And so the fourth is the sum of all of these different things, which you're adding over the number of x's versus the number of y's. For the exponents on each separated term add up to that 4 because there's 4 equations, and everyone gets an x and everyone gets a y. So anyway, the binomial coefficients, these binomial formulas will be useful when we do the binomial distribution. It's a little bit more involved application with our counting and our stories and things like that, but it can be useful as you get to it. Right? Now the sum we've seen was 2n here, right, in this chart. We have the general formula here. Here's the general formula. Right? In that Pascal's triangle, this general formula can give us the 2 to the n result. Right? If we let, as a special case, if we let x equal 1 and y equal 1. Right? Let x equal 1 and y equal 1. Right? Then x to the power and y to the power, those are just 1. And then we're left with a sum going from 0 to n of n choose k. So from going from this special case, this general case, put 1 and 1 in there, that's 1 to the n. Oh, well, that's 2, sorry, 1 plus 1 is 2. 2 to the n. And then we get there. 1's go away in here when we get that sum. So back in this adding across the row, that's how we got the 2 to the n. Right? This is, if you have 4 elements, how do you choose them all from one side, all x's? 4 choose 4, 4 choose 1, 4 choose 2, 4 choose 3, 4 choose 4. And you add those up. That's the way a number of ways of dividing that up. But anyway, that's a little bit more involved example. That's what I have for today. Any questions about things? So, all right. So, you get your homeworks? Be sure to turn in your homeworks. You put them in a pile here. I have my stapler in case you need a stapler. I think it has the staple in it.
It's like, I gotta go to Staples, we can play that.
I'll be in until this afternoon. Yeah, you can be fine. Thank you. Great. I do. I have a phone call I have to take, so I can have 12:30. Works. Would you like to come by then? Okay. Sure, I'll be in a second.
Thank you.
Yeah, thank you.
Hi.
Yes.
So I'm on the softball team.
Okay.
And this is just kind of like a rough, guaranteed to change game schedule.
Oh,
We'll
okay.
Miss classes, but
Yeah, and so just stay, in touch with things that are going on, kind of while you're.
and I will, as soon as I find out when games are switched, I will absolutely let you know.
Yeah, we'll put things on,
So-
on Canvas, and, Integrity should record, and, handing in things
Okay,
either
good.
early or asking for an extension on those 2 times, it should work out, I think, so.
Okay. Thank
What
you.
position do you play?
I play first.
First base, really?
Yes. Yes.
That's an exciting one.
It is. It is. I'm guaranteed to have something to do.
Yeah.
Thank you.
Yep,